Welcome to the 8th in our series of videos having a look at how GAGE is structured and how it works. This particular video we're going to have a look at particle effects, particle systems. They're one of the more interesting aspects of games in as far as they're simple in many respects, and you can get a lot of interesting and apparently complex visual phenomena and visual things being simulated using particle systems. As is usual in this here, we'll talk a little bit about the theory behind it. There is actually a video you can look in a bit more detail on this, and then we'll delve down into the code to see how it's implemented inside GAGE. First thing, just to really highlight, there's lots and lots of different types of particle system, and what's shown on the screen sort of shows you a number of sort of circular style ones, but that's only scratching the surface, and I'll show you sort of a demo program as an online one, which gives you an indication of some of the common particle systems that are available. I have a few pictures from actual games that again will help illustrate this. So whilst here we have a 3D system, the explosions or the smoke you can see in the back, they're particle effects. So they're effectively, there's two particle systems, one giving the appearance of sort of a fireball, the other one of some sort of fragmentation and a sort of a debris or dust cloud following on from it. The same chunk of code would actually simulate both of these different effects. Next example we have here is sort of Mario 1, and if you look at Mario Luigi at the bottom, you can sort of see there's sort of puffs of smoke, if you want to, following after them. So in terms of if they move around, they have an effect indicate that they're moving over ground. Again, that will be managed by a particle system. And actually quite a lot of how this is managed and how it's simulated is exactly the same as to how the explosions were simulated in the previous screen. And the last example I have just really is to highlight in a lot of games, be it really any type of game, you can see on this particular screenshot here, there are particle effects galore. And actually for games, if they're trying to get across the excitement and the interaction, quite often particle systems are your go-to mechanism for doing this, almost to the point where they sort of dominate the scene. So they're used very broadly. They actually are reasonably simple things to actually implement. Some of the complexity you can get in terms of how do you do it fast and efficiently, or if you're getting into things like volumetric effects or other related ones. But in its heart, a particle system, and you can sort of see a little bit of it here, you have a small number of images, particles, and you have a large number of those, and you draw them on the screen. And the number of them and some variations maybe in the size and the position and how you combine them together, they are the things that actually bring to life, so to speak, the particle effect itself. So if you look at this particular image on the screen, it's of an explosion effect. But if you were to look at any of the the projectiles that are going out from the explosion, and you look at those, you'll notice there that these sort of a little circular style images. So if we're actually doing this, we have a number of individual particles, each particle drawn as a little bit on its own, that we are combining together. And the magic arises from being able to combine them together and to be able to evolve them over time in a way that if you play the thing, it gives you the appearance of, in this instance, an explosion or a plume of smoke or anything like that. So simple premise. I suppose the complexity comes just in terms of tweaking the value so that it looks right. Now, I'll show you a few other examples. This is from sort of a nice little website. So you can see some of the different particle systems. So we have ones here. This is their Meteor Effect, where you have a certain density drawing in the center. The individual particles then will sort of pass off from it. They'll sort of fade out or change over time. Fireworks, you can see it actually most easily here. So you have one emitter at the bottom. So emitter is where the particles are born from. And the whole bunch of particles, each of these colored circles is a single particle. You can see from this here that there's a degree of randomness in this, but there's also a degree of predictability. So all the particles here are shot up, but within certain bounds. They'll have a certain amount of random variation within it. And you've got the colours. Over time, particles can shrink, or can expand, can shrink, can fade out. So there's different ways of doing it. But this one nicely shows you each of the individual particles. Fire itself, so whenever I trigger the fire one, you can see the dots appearing on the screen just as the particles start to come into existence. And then when you have a sufficient density of them, because you're drawing them on top of one another, it sort of gives that type of thing that we can sort of view it as a lazy fire that is brighter at the bottom in terms of the colour tint that applies. It drifts up. We change the colour tint to sort of simulate it becoming less hot and more smoke-like. So simple premises, just depending on how you draw them and the values that you use, you can get this to give a reasonable approximation of different effects. Galaxy one here, so similar to the Meteor one, just we're changing how we actually create the particles and then how they move. So this here you have sort of circular, giving you a spiral type effect. Snow you can quite easily see the thing then. So we create them at a certain point. The particles in this case are affected by gravity. You can have random sizes depending on how big or small they are, and they just sort of drift down the screen to simulate snow. Bubbles, it's almost in the opposite direction here. We have bubbles created at the start, a bit more variation in terms of how they move. They sort of go from side to side and they go up the screen. And you can see sort of the brighter bits just depending on when they overlap, how they're actually drawn together. Water geyser, similar principle. You got an initial emitter that throws them up, but then we have the particles being affected by a gravitational force. So they're pulled up, then they're dragged down and they fall down as this particular effect carries on. And ribbon's the last one. Again, you can see a bunch of particles that are spun out a certain direction and they change their colour over time. So that's an example of some of the different types of particle system that's available. There'll be one reasonably simple piece of code that makes all of those things possible. So we want to have a look now inside the GAGE framework, and we'll see how and where we implement particles inside this here. So I'll run it first of all, and then you'll be able to have a look at where we have our particle effects. The minute is built into the spaceship demo. So if we go to the spaceship demo, inside this one here, we have the AI controlled spaceships that as they move, they have sort of a particle trail behind them, depending on the move. For the player, as we move the player forward, it has two particle effects built into it. And whenever I release initially the speed, it sort of peters out and then comes to a stop. So the current one we have then has basically a particle effect that we're playing many times and is attached to different objects. And as things move around inside the game, or objects have the particle effects associated with them. Okay, now that's what we want to have a look at, and we'll see how it actually does this. In terms of where we want to go for our code, so the main setup is within GAGE. We can go into our engine. We have a particle package inside this, and you can see here all of the main classes that we're interested in. So we have a particle. We have particle settings that tells us about particles. We have an emitter. So an emitter is something that releases particles. So in the demo, I'm just after showing you there inside GAGE, each of the spaceships would have an emitter as it moves around, or for the player spaceship where there was two streams emerging, that would be two emitters. We have emitter settings, so it tells us how the emitter works. And we have one particle system manager, which helps us manage all of our different particle systems. So they're the classes that we want to look at. The other relevant ones in terms of the demo that they're linked in with is inside our space demo, and it's both the player spaceship and also the seekers as a class. These are the things that contain particle systems. Right, now we'll start off first of all by having a look at the particle class itself. So we're talking about particle systems, so this is a good point to start at. Particle class, it has to, and if we were to go back and have a look at say this setup, bring it through to here. Actually, I'll paste it in the top for this particular demo. So whenever they are being played, you can see the different particles as they are created on screen. Sometimes they have different colors, sometimes they move in different ways, they look a bit different as well. So if we're going to have a particle class, we want to create a class that gives us enough flexibility to manage all of these different types of particle. Now there's no one right or one wrong way of doing this. This is the particular one that's written inside GAGE. It will capture a certain set of properties and values. It's not an exhaustive set. You could have other ones into this. But let's have a look at our particle class then. So single particle that's managed within an emitter. So an emitter will create a particle, and that's one combined with many other ones will go together to form a particle system. So what do we say? A particle is defined by a size. So it has an X and a Y size. So some can be bigger than others in terms of particles, depending on what effect we're simulating. Small particles, big particles, could be variation between them. They have a position in terms of an X and a Y position. Again, that's fine. They have a velocity. So the particles move over time. So again, that's fine. Each particle can have a velocity, and that velocity can itself be changed depending on how we simulate the particle effect. We have an acceleration. So sometimes if you think about the one with gravity, you have an accelerated value pulling the thing down. If it's an explosion, you might want to give an initial high velocity pushing everything out very quickly, but then to apply a negative acceleration, so it shoots out fast and then slows down as it expands out. So we can give our particles an acceleration. So the particle is basically a bitmap. We have an orientation. So all of these things don't have to look the same. We can rotate them around. It has, or can have, an angular velocity. So this determines how quickly the particle effect is rotating, and sometimes you do want it to be rotating. It has a scale. So when we're drawing out each particle, they may change their size over time. They may get bigger or smaller over time. And if we create two particles, they may differ in terms of their size. And we'll use the scale then as a way of controlling how big this particular particle instance is. We have a scale growth value, and this is a particular, again, there's different ways of doing this here. This one assumes you have a normal scalar value that determines how the scale, the actual scale, the size, changes from one update to the next. So depending on the value you can set here, you can either keep the scale as a fixed value, or you can start making it bigger or making it smaller. Particles, if you think about them, they create, they do something, and they sort of either they fade out to nothingness or maybe they leave the screen, but they have a lifespan. A particle might exist for 2, 3, 4 seconds, probably not much longer than that, but our lifespan then is going to tell us how long each particle is going to remain alive as part of this simulation. And again, you can put variation into this here. Some particles may live for longer than other types of particles. We've got a time since birth, and this is the thing that lets us tick up to count how this particle, how old it is relative to defined lifespan. Whenever it gets to the end of its life, we're obviously going to remove it. We've got two things here, fade in by and fade out from. And again, this is specific to this particular implementation. So you generally want to avoid things popping into existence. So just suddenly displaying a bitmap or suddenly not displaying a bitmap, because that's the type of thing that a sudden change, our eyes will be attracted to that and will notice it. Rather, if you fade things in from a 0 alpha up until sort of it's fully in, and then that sort of gradually makes it appear and look much nicer. And then when it's approaching the end of its life, you don't want it just suddenly to disappear. You generally want the thing to fade out so it looks to sort of subtly disappear. So fade in by, you can basically put in a value. If I say 0.2, it means by 20% of the lifespan, it has to be fully faded in, and it will go from 0 up to full fading in for that period. And fade out from, if I said from 0.75, it means when it gets 3/4 of its edge, maximum edge, it'll then start slowly fading out in terms of changing its color tint until when it's completely reached the end of its lifespan, is completely faded out too. We actually have a fade value itself, which determines at this point in time how much we're fading it out by. And finally, we have the bitmap that is going to be used for this particular particle. So particle is a whole bunch of properties. There's quite a few of them because depending on how we set up and configure these values, we can get interesting and different effects coming out of it. You'll notice then we don't actually have a constructor. Rather, we have an initialize method. So there's no constructor in this. And this also ties into an important aspect of a particle system. Particle system, you will have hundreds, can be thousands of particles. Each particle lives for a couple of seconds. We most certainly do not want to be creating objects, large number of them, which live for a couple of seconds and then are discarded. So we're going to use a pool. We will have a pool of particles and we will take ones from this pool, we'll initialize them, give them a set of values, use them in the simulation, and then whenever they've expired, time's run out, we will put them back into the pool. So we will recycle and reuse our particle objects to save us creating and then discarding a bunch of particles, because that would be quite inefficient. So initialize is similar to the constructor. Basically, you just pass in all of the different values, size, position, velocity, so on and so forth. It stores them. That's it. We have an update method, so we can go to a particle and we can update it. And this actually is fairly similar to the sprites update. So if we have an acceleration, we use that to update the velocity. We use the velocity to update the position. We use the angular velocity to update the orientation. We're going to be changing potentially our scale, how big we are. We use our scale growth to change the scale. We add on how long it is since we were born. So time since birth plus whatever that time step is. Then there's a little bit of a calculation here. So we've got two values, fade in by and fade out from. So depending on how far through our lifespan we are, we're either in the fading in phase, or we're in the fully visible phase, or we're in the fading out phase. So the code here will simply say, okay, well, what is my percentage time? And use this here by fade in and fade out from to work out what the fade should be at this particular point in time. So that's what it does. We have a convenience method isAlive, which we can actually call to say, for this particle, is it still alive? In other words, is it still part of the active simulation? If it's not alive, it means this particle, we can remove it from the active simulation, don't need it anymore, and add it back into our pool of particles. So that's what a particle contains. If I have a look at the particle settings file, so we'll do that next. Particle settings basically tell us how we will create and configure our particles. So it's going to, for a particular simulation, be this smoke, be it fire, something like this, it'll be a set of values that we will use to control the types of particle that we initialize for that effect. So this is, again, it's just a bunch of control values. And you'll see this. So we're going to have a name. So I could say that this is my smoke particle settings, or it's my fire particle settings. I've got values in here for the width and the height of it. This is in terms of my game object. So inside inside the actual game, how big should I be displaying each of these particles? And you'll notice then for what you see down there, you're going to have, for example, velocities. I've got 4 values here that define that control the types of velocities that my particle will be assigned. I've got minimum and a maximum. And you'll see minimum and maximum really for a lot of the things as we go down through this here. And that's important. One of the reasons particle systems works is that there's random variation, but within bounds. So you randomize a lot of things, and that sort of gives something that's not predictable, looks slightly chaotic to our eyes, but we're much more accepting then of this variation. So for whatever particles I'm doing, I can say whatever the minimum and maximum velocity direction is So you imagine this in terms of 0 to 360 degrees. If I had 0 to 360, it means these things can shoot out, have an initial velocity in any direction. If I said from 0 to 90 degrees, then all of my initial velocities will be in a certain direction of travel. That's useful because sometimes I want particles to go out in all directions. Sometimes I want particles to shoot up in a certain direction. So by specifying my direction vectors here, I can control if it's narrow or how broad the launch direction for our particles are. Likewise with minimum and maximum velocity magnitude. So I can specify the direction, I can also specify the speed. I can say that some go out fast, some go out very fast, some go out a little bit fast. I can be as precise or as open as I want to be in that. Similar for acceleration. So for the acceleration we apply, we can specify what direction of travel we want it to be in. Sometimes you may want gravity to pull it down. I can specify minimum maximum acceleration value if I want to do that too. Minimum maximum orientation, if I want them all to be oriented the same way or to have a bit of wiggle one way or the other, or to have any old random orientation. Likewise with angular velocity and scale growth and lifespan. So again, some may live for slightly longer than others, or I could set min and max to be exactly the same value if they are precisely the same between them. I can have fade in and fade out, again varied as well. Some will fade in a bit quicker than others, some will fade out a bit sooner or later than others if I want to do that. And bitmap, I don't have any. You could put in a whole range of bitmaps if you wanted to have several different options. The particular implementation here says for a set of particle settings there's only one bitmap that we're using, but that's just an assumption. You could enrich that if you wanted to. So again, particle settings is a bunch of values. That's it. What I have down here, I do actually have a constructor for this because we will build, generally speaking, one set of particle settings. We'll have one in memory and we'll use the settings contained within that to define how the hundreds, thousands of particles associated with that particle effect get to be initialized. We're using JSON here. So if I into my assets, into text, into particles, I can see my, for example, thruster particle. It's a JSON file and it will then contain all of the different settings inside this here. So I have over here my thruster particle, width and height, minimum velocity, minimum different direction. So you can see there, for example, for the thruster particles, I'm happy for them to shoot out in all directions. The velocity is a random value between 0 and 5. The magnitude of the velocity is a random value between 0 and 5, but any direction in terms of the magnitude. So the constructor for this you pass in the JSON file. It simply goes through the JSON file. You can see the assumed structure up there. Extracts out the value and stores them into the values that we have at the top of this. So that's all that it does. It doesn't really do anything much more than that. And it's actually by changing the values over here that we can have an effect. Okay, so let me just run this then, and we can see what some of the values, how we can change them. So at the minute, in terms of the default configuration, whenever I move, you can see the particle specs go out at the back. Over time, the particles actually decrease in size. So the scale they have here is that the longer they go, the smaller they become. There's a little bit of random jitter and variation as it moves across, just in terms of the angle that they're going out at. If I wanted to, I could then change these values. So over here, width and height, I could make them a good bit bigger. So there they're going to be slightly wider and higher than they are by default. What other things I could do? I could give them a minimum velocity of 15, maximum velocity of 25. So in that sense, they're going to shoot out again in any direction, but with a stronger force for that. Scale, I could, well, okay, so let's make it live a little bit longer. So we'll say they live from 1.4 to 1.5 seconds. So by changing those particular values, when I run this again and I have the ship moved, you can see that we have bigger particle effects. They are, because we increased the size, they're living for longer now. As I go around it, you can see the actual plume persists about for a slightly longer period of time. And whilst initially all of them are sort of tying into the velocity of the spaceship, you can see for the ones that leave behind it, there's more variation in terms of how they shoot out from it. So by changing a few configuration, a few values, you can have quite a radically different effect overall in your actual simulation. I'll just set that back. Okay, so that's particles and the particle settings. The next one we want to have a look at then, let's go into our emitter. So the emitter is a little bit more of a complex class, and there's emitter settings. Now we'll start off with emitter settings because this gives us some configuration values that we can use to understand what an emitter does. And we have a thruster emitter JSON file, so I will move this one across so we can change some of the values inside it. Okay, an emitter then. So the emitter is the thing that controls how individual particles are created and helps configure some of the values inside this. So anytime we create a particle, the particle settings will determine a lot of the values, but the emitter itself can also determine how many things get to be created and can also tweak some of the settings of each of the individual particles. So we'll look at our emitter settings first of all, and we'll see the options we have inside this. Now, these are common options, there's not exhaustive options, there's different ways you can do this. First thing then is emitter settings. We have two modes, burst or continuous. And if you think of this here, so the ones we have at the minute are in the GAGE demo are continuous. So it means that as long as the ship moves about, you have a continuous stream of particles being generated. Some other effects, for example, explosion effects, they provide a burst of particles right at the start. So you create a large number of them and they all shoot off in different directions. But that's about the extent of it. So a burst particle effect is a one-off particle effect. It's ideal for explosion type things where you want to have something suddenly appear and then to disappear or disappear from it. Likewise, if you had a character jumping down onto the ground and you wanted to have sort of a little sort of plume of smoke, is when or sort of smoke-like effects, whenever the character hits the ground, that would be a burst effect as well. Collision happens, you'll display some particles to simulate that collision. So we can control for how we're doing this here. If it's burst mode, in which case we give a large number or a certain number at the start, or if it's continuous, where we say we want to have X number of particles per second. You have the difference between additive and alpha blending. So additive, alpha blending is just normal blending. We have bitmaps here, and we're just combining them as we normally would combine them if there's transparency or not. We're just using the ordinary alpha blending. If it's additive blending, then we add it to the image, and it gives then the appearance of it being brightened. So you can see you also have actually let's make this change. So over here the blend mode at the minute is additive. If I were to change it to alpha and then to run or demo again, you can see the difference. So now whenever I'm displaying the particles, I'm actually just displaying the bitmap as it stands. So you can see it looks purpley. Fair enough, if I find the bitmap for this here, I'm not actually sure what it is called for this one. Actually we can. So let's go to our thruster particles. It is purple dot. So purple dot is our particular image inside particle. Purple dot. Okay, there you go. So purple dot is the thing I'm currently displaying. So as I move across, I'm displaying a whole bunch of purple dots behind this, and it looks like it looks on the screen. But if I were then to change this to additive, it means that when I'm drawing them, I add them to what's there before. the important emphasis of this is you keep drawing on top of things, as long as you're not just drawing black, it gets brighter and brighter and brighter up until the point where it'll appear to be white overall. So additive brightens the image in general. So now when I move around, you can see that it looks to be a bright white because several of them are being combined and drawn on top of one another, and as they separate out, it sort of gets returned to a more purpley color at the end. So in this sense, additive actually looks nicer in terms of how we do it. Acceleration mode can be aligned or non-aligned. So to find the acceleration mode, if it's set to align, then any generated acceleration will be added in the direction of the current particle velocity. So sometimes when you create particles, you can give them a direction of travel. They can shoot off in any direction, and you could have them accelerate in any direction as well. So they can shoot off in different directions. Sometimes you want the acceleration to be aligned with the initial direction of travel, either to make it speed up faster than that, or actually to make it slow down. So if you're thinking about, let's say, an explosion effect, there you might create a bunch of particles. You want them shooting out in different directions, but for an explosion effect, you want it to move out very quickly at the start, but then to slow down as it moves out. So it moves out quick and then slows down. So in this sense, you would be saying it has aligned acceleration, but as a negative acceleration, the acceleration will act to actually slow the particle down. So again, depending on the type of effect you're doing, you can set up these values. So they're sort of important distinct variations of it. Okay, so for a particular emitter, we give it a name, so we can refer to this and use it. We say, what is the mode, burst or continuous? We link it into particle settings. So an emitter is going to release a certain type of particle. This implementation assumes there's only one type of particle it will release, and we want to get the settings for determining how we configure those particles. We have a min and a max particle density. And there's dual interpretations here. If it's burst mode, this is the minimum and maximum, so again you pick a random number between it, the particles that are generated right at the start. If it's continuous mode, then this is the minimum and maximum number of particles that are generated per second. Blend mode, how we want to blend it in terms of drawing it. Acceleration mode, how we want these things to be linked to acceleration or not. Velocity bias. So if set to 0, no velocity bias will be applied. So basically in this case here, we can control based on the entity or the thing that we're doing, do we actually link any velocity bias into this here? So we can use this here. If you have an object that's moving and you want the particles to be created relative to that object, then you can do that. So the minute's got velocity bias of -1.0. Now if we were to change this to 0 for sake of argument and run it, so in this case we're not applying any velocity bias. So as the spaceships move around, the particles themselves are simply get to be created. So there's a small difference between it in terms of how we do this. Okay, so if we want to have a look then maybe how we could change some of these values. So if we were to change, so for example our particle density from 25 to 30 per second to 2 to 3 and run this. Now for this particular one here, you can see now as the ships move around, they're only sort of popping out 2 to 3 particles every single second. So as they move here, we've reduced the number of ones that are generated. So we're back up to 25, and 35 means you would get the same appearance. Now I could go to 250 to 300. So now they're generating out, up to 300 particles per ship, and it just means that because there's 300 of them, it looks a lot whiter than it was before, but it's not massively different than 25 to 30, apart from being a lot more inefficient now because we have 10 times as many particles that we are simulating. So depending on how you do these things, it will control aspects of how our particles get to be created. And then that's back to the normal one, have 25 to 30 of them generated per second. Okay, so bunch of settings. The constructor for this does the same as the other one. It simply goes through the JSON file and tries to load in the different values, and that's our configuration parameters for each of the emitters. So let's have a look at the emitter class itself. Now the emitter class is a reasonably long class, and there's not so much complexity inside it, but there's a few things we do want to have a look at. So we'll get rid of these bits over here. So an emitter is responsible for creating, so it actually will have to create particles. It's responsible for updating. It's going to have to go through the live particles, make sure they update themselves, and dispossessing, for basically recycling the different particles that we have. Okay, so an emitter is linked to a set of emitter settings. That's unsurprising. An emitter has a position. So if you think about the spaceships, that position is relative to the spaceship. Whereabouts does that emitter reside? Where are the particles created from? And the position of the emitter can change, or it could be fixed. We have a last position. Now this is relevant if we have a moving emitter. So if something's moving around, for example, as it is in terms of the spaceships, it is actually important to remember where you were for the last update. And the reason for this is that if you have a moving emitter, it's normally linked into continuous mode of emission. You're constantly releasing your particles. And to do this smoothly, you want to, if you're creating particles, you want to create them over the period in space that it's moved from last update to current update. You don't want to create a big clump where it currently is. You want to sort of spread them over where it's moved since the last update. So it gives you a smoother release mode. We have an array of particles. So these are going to be the particles that this particular emitter manages. There's different data structures you could use for doing this. It gets into swings and roundabouts in terms of how the speed at which you can access these, the speed at which you can add things to this, the speed at which you can remove particles from it. And it is swings and roundabouts because it depends on the particle system as to where you'll spend, or as to where the relative costs of iteration, addition and removal are going to kick in. It's an array. We will have a certain number of particles that are currently active. So this particle storage, it may be enough storage for 500 particles. We may only have 34 particles active at this particular point in time. That's fair enough, but that tells us the number of ones we need to be worried about. We have a particle storage cleanup threshold. So this basically says that for our particles, now remember, why do we have this here? When we create a particle, and we add a new one in, it's initially alive. Over time, as we evolve it, some of the particles will die and will expire. So if I have 100 particles at the start, they may all be initially alive, but as I go through the simulation, then some of them will start dying, other ones will start dying, and eventually all of them will be dead. So I need to have some trigger point that says, when I'm looking through my particles, if I'm seeing less than 75% of alive particles, so I've got at least 25% that are dead, at that point I will trigger a cleanup, and I will go through and I will reshuffle things inside the array just to get back to ones that are all alive. So by changing the value you have here, it's a trade-off between memory, amount of memory that you're holding, versus the amount of time you have to spend cleaning things up. We haven't yet looked at the particle system manager. We'll do that in a bit. But an emitter is managed by a particle system manager, unsurprisingly. And we're going to have, again, for drawing this here, a sort of internal one that lets me work out. If you imagine an emitter might have 100 particles associated with it. Those particles will be moving off through your game world. So I'm going to bound all 100 of my particles inside a rectangle, and I'll use the rectangle size will be based on how far the most visible, or how far the furthest particles got from the emitter position. That's effectively going to give me a bound. So inside this I might be able to see particles, outside of this I definitely won't be able to see particles. And when I'm drawing out a particular emitter, if this rectangle isn't visible within my viewport, I'm not going to bother drawing out anything to do with the emitter because none of it will be visible inside the viewport. So it's in here for efficiency reasons. And I've got to track this. So as my particles change, I need to be able to update the visibility range. Got a constructor. Constructor, you need to pass in a particle system manager, the JSON file, and where you originally or initially want the emitter to be created, and we do that. Different versions of this one here. Here's the one here, so it does the actual thing. We store the different things we put in, we set the position, and we have a default last position to where we started at. We're going to go through initially for max particles to work out what the max particle density is, and work out then if it's continuous, and also the maximum lifespan. We'll calculate another value here. So basically there's a bit of code that tries to initially work out for this emitter what's the maximum number of particles that we would have to deal with, depending upon density, lifespan, things like that. When we've calculated the maximum number of particles, we use this then to define the size of our particle storage. So we know for this particular particle effect that we've got enough storage to store the worst case scenario. Worst case in this sense, if I have the maximum number of particles active and live at a point in time. However, initially, number of particles is 0. Fair enough, we got some methods for setting the position or for getting the position of the emitter. We can get the number of particles that are currently includes number of alive particles and those recently expired but are yet to be released. So you need to be careful just in terms of what you're using this for. But it's the number of particles, alive or dead, that this particular thing is managing at a point in time. You can get access to the particle storage if you want it, and you can access to the emitter settings if you want to tweak and change those. And you can also get access to the visible range of that particular emitter, just how far particles have moved out. Number of particles to add to accumulator. So this is you'll see this being used later on. But if you're dealing with burst mode where you're creating a certain number of particles per second, now it may be a large number, which means normally for every single update you'd be creating 1 or more particles. But it could also be a small number. It could be 2 or 3 particles per second. Which means that from one update you probably won't be creating anything a 20th of a second later. You probably won't be creating anything a 20th of a second later. You might be creating 1. So we have an accumulator here just to let us, if we want to have a small number created over time, to deal with those fractional bits depending on how the number of updates we do. Here's our update method. We're going to do a few things. So we first of all work out if we need to add in any additional particles, and if it's burst mode, no we won't. If it's continuous mode, yes we will, or yes we might. We have a look here to see, are we applying gravity? So if we are applying gravity, then we're going to go to our particle manager and say, well, tell us what gravity is, please. And then we'll go through the particles which we're currently managing, and we will make sure that we update its acceleration vector to now include an element then that is gravity added on to it. Update the particles, keep a track of how particles are from the emitter. So over here we've got two things. We're going to update the particles, but when we update them we're also going to check to see, well, how far are you away from the emitter, and we'll keep a record of the things which are far away or at the outer bounds, because this will enable us to update the bound that fits around the emitter. So count for the number of updated particles. We need this here because we're going to use this here to work out, do we need to, if we have a sufficient number of dead ones in our array, then we will rejig the array just to have ones that are alive. So number of updated particles, that's important because that tells us the number of live ones that we've seen. So what do we do? Visible range, we initially set this just basically to the emitter itself, to what we have here. We go through each of the particles, we get the particle out. If it is alive, so the particle we bring out might be died, might be alive, but if it is alive, what do? We go to the particle and we tell it to update itself. So this was the method we saw that updates acceleration to velocity, velocity to position, and so on. And we say, yes, we have one alive particle, let's update it. We then check down here, now that we updated the particle, work out where that particle is. Where is the left, right, top and bottom side of that particle? And if it's one that is moved further away from the emitter than any other one, then we will update our actual bound. So we're keeping a track of just how far the particles have moved away from the center of the emitter, so to make sure we have an accurate bound in terms of is it visible or not visible when we're drawing out the emitter. We'll have a method here for considering if we want to remove any particles. So this is where the percentage of alive and dead has got to the point where we think we need to get rid of the dead ones just to have more live ones in our array. And last position, now that we've done our update, we say that the current position that we're updating this term is going to be our last position on the next term. And we return the number of particles that we updated. So reasonably straightforward. Consider adding particles then. So this is the thing that works out. Do we need to add particles in? We have a time for the time step. So there's two things. If we're in burst mode and we have yet to add any particles in, so in other words, we've just created it, it's the first time we've done it, we're in burst, but we've yet to add things in, then we are going to call our method add particles, and we'll randomly add in between minimum and maximum particle density. The else means we are in continuous admission mode, and then we are going to work out number of particles to add. We're adding onto our accumulator because this might be a fractional bit depending on how many particles per second. Anyway, a random number between our minimum to our maximum, scaled by the amount of time that's elapsed for this particular update. Any time our accumulator exceeds 1, then we will add in the relevant number of particles, and we're going to then update our accumulator just to keep any fractional bit that's left at the end to make sure we're smoothly adding in our particles over time. So far so good. For adding in particles then, we've got a few private things up here just to make sure we're not creating vector objects which will then be discarded at the end of it. But add in particles, we can pass in the time step and the number of particles we want to add in. There's a difference here in terms of the emitter mode, if it's burst or if it's continuous. If it's burst, then everything gets set at the particular position the emitter is at, and we don't need to worry about any offset. If it's continuous, then we do, because we want to look at where we were last time, where we are this time, and if I'm adding in, let's say for example 4 particles, I'm not going to add them all into my current position. I will step those 4 across the vector between where I was to where I am, so it's smoothly spread across that area as well. I check to see here, am I applying any velocity bias? If I'm not, then fair enough, the velocity bias, the particle set to 0. If I am applying a velocity bias, then I work out my velocity based on how fast the emitter is changing. So depending on where I was this turn compared to last turn, that gives me my velocity. I will actually turn this into an actual vector, and I will use that then to scale or to determine the velocity bias that I have scaled by the actual step time itself. So I apply velocity bias if I want to. So these are setup ones. Initialize and add the particles. So down here, I've sort of done my initial setup. I say, okay, how many particles am I adding in? So I want to add these particular ones in. I work out the number I have in my particle storage. If need be, I'm going to increase things if I do need some additional storage. If not, I'm going to go to my particle system manager and I'm going to say, here, give me a particle from your pool, please. That gives me my particle. I'll initialize that particle in terms of setting all of the initial values. We'll see that in a second. And I then add it into the particle storage for this particular emitter. And I update my particle position to add on the offset. So this means I'm then stepping across. So if I'm adding in 4 of them, I'll add in 1 over here, and then the next one, then the next one, then the next one to string it across from the previous to the current position. For initializing the particles, the next thing, so this is called within my add method. Again, I have a bunch of things here defined internally just to avoid object creation costs. Initialize the particle, it's a longish method, but it's very straightforward. It basically says, okay, you have a size, width and a height. For example, for the velocity direction, I got a helper method here that picks a random direction between the minimum and maximum directions and stores it in the direction itself. I've got another helper method that says, okay, for the speed, well, pick a random variable between the minimum and maximum. That gives me my speed. I can then set my velocity to be the direction that I calculated times the speed that I'm working at, and I add on my velocity bias if I'm using this particular one, depending on the values that I've created above. So in essence, this whole method here, Initialize Particle, will simply go through and to work out what initial values do we give to our particle. This one here is for the acceleration mode. If it's aligned, then I want to make sure that my acceleration is relative to the velocity of the particle. So I'm applying a little bit of threshold here, just in case I have sort of, you get down to zero accelerations or near zero velocities. So I want to have a little bit of threshold just to make sure I can do the maths correctly on it. Anyway, if need be, I will set the acceleration to 0 if my velocity is 0 and the thing is aligned. Other than that there, I'm going to work out what direction my velocity is in, take this direction then, and then use that direction to actually apply an accelerative force relative. So I do the magnitude, but I apply it in the direction of the current velocity of the particle. If it's not aligned, then I don't need to worry about doing that. I just say, well, give me my acceleration direction, minimum, maximum, pick a random direction, pick a random magnitude, and set my acceleration to be that. Okay, so we can do this particular setup as well. What else do we have to do here? Determine the orientation. So random number between that, angular velocity, random number, scale and growth scale, random numbers. Lifespan, fade in, fade out, random numbers. And then finally, when I've calculated all of these random numbers, but for this particular particle, I go to my particle and I call the initialize method, and it just basically stores the values in the particle, nothing more than that. Next method here is consider removing particles. So this was the one that at the end of my grand update, when I've gone through updating all of the particles, if I feel that actually I've encountered too many dead particles, which are just wasting my time iterating over, once I get to a sufficient number of them, I'll remove them from the array. So consider removing particles, and I pass in the number of actual live particles that I encountered. And I have a check here, first of all, that works out that, well, two things. If the number of updated particles is 0, so in other words, I have no live particles, then I definitely want to make sure I remove anything because there's nothing left to update. Or if the percentage, if you like, of alive versus dead has exceeded my cleanup threshold, then I also want to do this. Effectively, what we have here is quite straightforward. We will go through our array of particles, some alive, some dead. If it is alive, then we want to retain it in the array. It's not going to go anywhere, and we'll increase our alive index. If it is dead, so if we encounter something that's dead, in this sense, we want to go back to our particle system manager and tell it to return to the pool. It can recycle this particular one, the index that we're interested in. So the one that contains the dead particle, we will release it. And just to make sure we've done this properly, so we don't have any sort of dangling pointers or hanging pointers to things, we'll set that array entry to null, and if need be, we can copy a live particle into it. At the end of this, then we've gone through. We're only now left with ones which are alive, so this is our new number of particles. Final bit there: if it's a burst emitter, then remove it if all particles are dead. So in this sense, if it's a burst and all of our particles have expired, so in other words, we created in burst mode, we created a bunch of particles. It's got to the point now where every single particle that we created in the burst mode has expired. It's now dead. In this sense, okay, so we're in burst, number of particles is 0. We go back to the particle system manager and we tell it to remove ourselves. So the particle system manager is responsible for managing different particle systems. We've yet to look at it, but this is one of the triggers where if our emitter knows that it's finished, we're only in burst mode, all of our particles have done their thing, then it will remove itself. The programmer doesn't have to remember to do it then, so it's really for convenience. Some utility methods: increase particle storage. So if we do need to increase the number of particles we have inside this here, there's a method for doing it. We'll create a new array, we'll array copy across, and we'll store the thing. We've got one for releasing all particles. So if we're getting rid of a particle system, the manager can then go to the particle system and say, here, release everything. So simply it'll go through any of the particles that are stored within it and add them back into the pool maintained by the particle manager. So it still gives us an emitter at this point, but the emitter that contains nothing. We got random between and pick random direction. These are just utility methods that if you pass in minimum maximum values, it'll randomly pick either a direction or a value between those minimum and maximum values. So that's the emitter. That's probably where the complexity resides in this particular case. Fair amount to it, but in the grand scale of things, maybe not that complicated. The last class we want to look at is Particle System Manager, and thankfully it's not that complex a class. So it's the one that's going to be responsible for managing the different particle systems. So what do we have here? With Particle System Manager, it belongs to a game. So a game is going to have its own particle system manager. Well, it can load things in, get access to different bitmaps. That's why we need that. It's going to have a list of emitters that it's currently managing. It's going to contain a few things for the number of particles that are updated and the number of particles that are drawn. We simply use this here to help sort of keep track of the number of things, so you can report it for performance management reasons. And it has a gravity value, so it assumes that all particle systems, if they are subject to gravitational force, that was one of the emitter settings, then we will use the same gravity value. So you can specify it here. It applies to all relevant particle systems then, or all emitters managed by this manager. If we create it, we simply store the game. We can specify the maximum size for the number of particles that we want to have in our reusable pool, and if need be, we can grow that or extend that if we want to. So does two things: set up the particle full and sets up draw, and we'll see those methods when we get down to them. Utility ones: get number of updated, get number of drawn particles, fair enough. Set gravity, fair enough. Get gravity, and get the game. So these are just utility methods for getting access to these things. Right, so emitter management. So as a particle system manager, it's going to have methods for adding and removing emitters. Adding an emitter is very straightforward. You just add it into the array list. If you're removing an emitter, a little more careful. You've got to make sure that we have this emitter. So if we find the thing, then we will go to the emitter and we'll tell it to release any particles that it has, so they can be recycled back inside our pool, and we will remove it then from our list of managed iterators. So we're not throwing away the particles, we will reuse those for any emitter that we remove. Update is actually very simple. We're going to have our counter. We go through each of the emitters that we have inside our array list. We get the thing out and we say to the emitter, okay, update yourself. And it's going to tell us the number of particles that it was actually updated. That's it. So the particle system manager basically just tells the emitters that it contains to go and do their thing. The rest of it then is actually more or less draw method. So this particle system manager is going to be responsible for drawing out the different particle effects that we have inside it. So as is usual for a lot of things here, we're defining some internal variables so that we don't have to recreate these every single time we draw something out. We got a bit of setup method to do for the draw, and this was actually called from inside the constructor. And we do this here because there's two ways we can draw, an emitter can draw particles out, either traditional alpha blending or additive blending. So we create one paint for normal alpha blending, and we create one paint for additive blending using the Porter-Duff additive mode. So we have those available and we'll reuse them anytime an emitter needs normal alpha or additive blending. Draw method itself. What do we have here? So a counter for number of drawing particles. We go through each of the emitters. We get the emitter out. We get the bitmap out for this here. We're storing a little bit about the size of the value for it. We're scaling it as well based on the particle width and size. So there's a little bit of configuration here just to make sure we can map these things correctly onto the screen. We're going to use an appropriate paint instance, either the additive or alpha blending one. Now that our setup's been done, we will go through the emitter and the particles that are actually managed by that emitter. So to get the number of ones that we're currently managing. If it's alive, then that's fair enough. There's something we can actually draw out. We don't draw out particles that are dead. They need to be removed eventually from our update, but we're not going to draw them out. So if it's alive, we get the particle. Now, we've got to go to our paint. Because we can fade our particles in and out, we're going to want to set the alpha on the paint with an appropriate fade value. And that'll depend on the fade value defined by the particle. We're going to use a matrix, because a matrix we can scale, we can rotate, we can do all of these things. We reset it, because each time we do this, we want to start again with a fresh matrix. We deal with some scaling if need be, so depending on this particle size. We can rotate it depending on whether or not the particle's rotated, and we can translate it. So we say whereabouts this particle is positioned inside our game world. And now at this particular point, we've sort of done all of our work here. We can draw that particular bitmap out to the screen and increase the number of drawing particles. And that's kind of it. Now, this is the simple version of draw, where you're drawing directly to the screen. It doesn't use viewports in this particular case, so it assumes that when we have a position, it's a screen position. The more complicated versions next is the one that says, okay, you're still going to draw it out, but now you're going to use a layer viewport and a screen viewport. So the positions here are not screen positions, they are game world positions. So it's going to be the same sets of steps as the one we've seen before, but with a little bit extra complexity throwing in for the game layers. So we see this here. Same idea, get the emitter. Now we have a visibility test. Previously, if I'm drawn to the screen, I assume it's going to be in terms of screen coordinates, it's probably visible. Now it's in terms of somewhere in my game world, and I've got my window into my game world, and I want to ask for this particular emitter, are its particles potentially visible inside my game world? So that's where I'm using the emitter visible range. And if it's not visible, so in other words, the regions inside which these particles exist, if they do not fall inside my viewport, then I'm not going to do anything with that particular emitter. I'll go on to the next one. If it is visible, fair enough then, I get the settings, I get the bitmap. I do a little bit more scaling this time in terms of scaling to the screen, because I've got to take into account my screen viewport and my layer viewport, so it's a little bit more involved. Still set up the paint as I do before. Still go through my particles as I do before, set up the fade, define the matrix value. Scaling here, so again I've calculated my screen scale is still the same. I rotate it, that's perfectly fine. Translation onto the screen, I've got to say, okay, what's the position in my world viewport? Sorry, in the game world, what does that correspond to on-screen position? So I convert my layer position into a screen position, and I draw to the screen position. So a little bit more involved, but not that much more difficult. Final things I have at the bottom are really just the particle pool. So we have the pool of particles, initial default size, initial default population. I can get particles from it, I can return particles to it, and I set it up to start to contain my default number of particles within the default size overall. So that just sets up the pool. Right, so we've been talking for a long time. Very last thing I will show you is just inside we'll just do the player spaceship because it's the more complicated example. So this is one that has two emitters, and you can see how all of these things come together. So inside my player spaceship is the thing that flies around. I have two emitters, one for the left, one for the right. I have a offset value for these particular things. So I'm going to have my movement emitter location, and because I have a left and a right one, I want them to be offset relative to that. So this tells me, okay, I know my center of the object, but I want to say whereabouts I want to have these different emitters being displayed. And in case of the actual demo that I'm running, they get to be displayed appropriately on the image. So that image of the red spaceship has a center point, but my two emitters are offset from that center point so that they appear to come from sort of the back of the spaceship. Okay. For creating the player spaceship, I define the two offsets. So they're both -20, so they're both sort of to the bottom of the image. One's to the left, one's to the right in terms of how I define these. And that just happens to map onto the right location in terms of game world coordinates. I create a particle system manager. So this particular object uses particle systems. It's going to have its own manager because that's what we can then draw to draw out our particle effects. We create our left and right emitter. So for doing this here, I say, right, let me create my movement emitter location. It's based on the position of the spaceship. Added on to that the left offset. So I say, okay, tell me where you're creating the spaceship. I'm going to offset that where I think the left emitter is going to be. I now create a new emitter. I say, well, you belong to this particle manager, and you want to use the thruster emitter JSON settings. And here's the location at which I would like you to be created. And I add that into the particle system manager. So it's now managing that one emitter. I do exactly the same with the right one. Offset to the right, create that, and then add that in. So at this point, our particle system manager actually maintains two particle systems. We've done all of our setup, and that's probably the hard work done, actually. If we're updating, so spaceship basically moves around. The few things that we do here, so what we have down here at the bottom is the update as it relates to movement. So two things. First of all, we want to update the emitters so that as the spaceship moves, we'll update the position of the emitters as well. So spaceship moves, the emitters have to move their location too. If they didn't, the spaceship would fly off, but the emitters would continue to emit particles at the same spot in the world. So we've got a mass helper, so we can offset about the center based on the position of the spaceship, and our left offset, so we know that's sort of 20 down, 20 to the left. We can rotate that particular by whatever orientation the spaceship has, and it gives me my new location. So using this here, I can update the particular location of the left emitter. Do exactly the same about the right emitter and give it its new position as well. There's one other thing that it does, and this comes back to the demo, and it shows you how you can tweak and again make this interactive. So at the start, both emitters are there, both emitters are being called, but no particles are being emitted. As I move across the screen, we've got a stream of particles. As I let go, the number of particles diminishes and then stops. So the number of particles that get to be emitted in this particular case depends upon the speed of the spaceship. The faster I go, the more particles I emit. So what we do here is we get the left emitter, we get the minimum and the maximum particle density. So this is the number per second, and we scale that actually by the speed. So the minimum is actually the absolute velocity, and the maximum is the 120% of the absolute velocity. Do the same for the left and the right emitters, and that means then that depending on your speed, that'll determine the number of particles that are generated, and hence the intensity of the simulation. And that's it, really. So anytime we're dealing with these ones here, that's all we need to do. The Seeker spaceship is going to be something similar, except in this case we will have one single emitter from the center. It also has an offset location because we want it to be at the back of it. We create it in much the same way as we did with the other one, except it's just one of them. We update it, and again, much the same way as we did with the other one. There's just one of them. There's no change here in terms of the number that are generated, so this always generates the same fixed number overall, so it doesn't really do very much. Okay, so far so good. The last thing, and then we are done, is in terms of this particle system manager. So the ones that are being managed, so inside the Player Spaceship, if we got to particle, now where we pass it in here. So this is actually, so when we're getting access to our particle system, we go to our parent screen, and it's a spaceship demo screen, and we say, here, can you give us your particle manager? So in this particular case, whilst the Player Spaceship and each of the seekers makes use of a particle system, they're actually sharing the same system overall. And the particle system they're using is one that is defined in the game screen. Now, it doesn't have to be this way. An object could maintain its own particle setup, but in this particular case, we said that for a game screen, we want to have one single parent particle system, and we'll make that available to any of the game objects that we have in this particular level. Fair enough. Where does it appear here? It's really just when you're drawing things out. Well, actually, sorry, updating things first of all. So anytime we are updating our spaceship demo screen, we update all of the game objects, and we go to our particle manager and we tell it to update any particles. Likewise, when we're drawing things out, there's our draw method down here. We'll draw out space entities, we'll draw out the player, and we'll also go to, at the right point, and we'll go to our particle system and we'll ask it to draw itself out as well. Right, that's a lot of information. I suppose there's a fair amount of detail this here. Not that difficult in terms of the overall complexity of it, there's just a fair amount of it. Wrap this up then. Particle effects, they're lovely things. They really are very broadly used inside games. They're certainly something you should consider adding into your own particular one, because you can, it makes it visually interesting, and there's lots of different effects you can do. Relatively simple from a programming point of view, really are. If you do want to put in a bit more complexity, not just for the sake of it, but for benefit, it gets into the performance management side of things. You want this really to be as fast as you can, particularly if you're dealing with tens of thousands of particles being active on the screen. You need to look at techniques there that are appropriate. You could be getting into things like volumetric, or having the particles interacting with other particles or other objects in your simulation if you want to do simple physics involving them. So there are things that can make it more complex. One thing if you are using particle systems is that you can get the code set up. You generally will spend a little bit of time, trial and error, tweaking the values. And it can be very sensitive to this here, that you can change one value and it quite dramatically changes the actual appearance of your particle system. And often the challenge is finding the right set of values that just gets the right effect that you're looking for. But fun things to play with, that's the important aspect.